Dissipative quantum mechanics. So, ladies and gentlemen, good morning. We proceed with our course, and there is another change of topic. In coming two lectures, we will go to the world of dissipative quantum mechanics. What is that all about? If you look at our classical world and our everyday life, dissipation, energy losses, is perhaps the most important and the most kind of intruding phenomenon which we observe. Most of the energy which we kind of produce with such costs, with such labor, actually get dissipated. The friction is the most striking phenomenon which we experience every day, every second, which is an apparent contradiction with Newton mechanics, where energy is conserved. So, this much dissipation in classical world, and the question we are going to address today is how it is compatible with quantum mechanics, or in more precise terms, how to build up a quantum mechanical description of dissipation and friction. That was a question which has been addressed in quantum mechanics in all details relatively recently. Like most of quantum mechanics has been founded in the 20s of 20th century, almost 100 years ago, while dissipative quantum mechanics has been developed only in 80s. Right. Before that, quantum mechanics followed the experiment which was available. So it was mostly about particles, single particles, which collided, which whatever got into excited states. It was mostly about more atomic physics, particle physics. And when I was in your age, I once just came to a quantum mechanical teacher. It was elementary quantum mechanics. We just studied oscillator, and I just I put the question. So, how to describe what would it be if I add a little bit of friction of to this oscillator? The teacher said, "Oh, that will be the subject of advanced quantum mechanics." Well, in several years, I took a course of advanced quantum mechanics, but eventually there was almost nothing there, except transitions, which we have studied a week ago. Transitions, it is a kind of common case of dissipation, most elementary case. But if you just have an oscillatory friction, you have a difficulty to see transitions. And for that, we have to think a little bit more. So what I am going to do today, first of all, we will talk a bit about dissipative classical mechanics. How to describe such an oscillator classically, what will be convenient tools for that. Then we understand that basically dissipation is not compatible with Schrödinger equation. One cannot just modify Schrödinger equation, introduce new terms to get dissipation. People have tried, it didn't work. There is, however, a solution for all dissipative problems in quantum mechanics. This solution is called boson-Bass. So in order to describe friction, in order to describe dissipation, one has to introduce very many external degrees of freedom, other degrees of freedom, which are commonly called Bass. What's Bass? Bass comes from thermodynamics, right? One can think of isolated system in thermodynamics, but that does not, that always keeps the same energy. Only if you put it into interaction with other degrees of freedom, with a reservoir which has a certain temperature and which is called Bass sometimes, only in this case you can have accurate description of thermodynamics. Good. So we find the solution, and then I will quantize damped oscillator. We will do it by hand because actually with our limited experience in advanced quantum mechanics, we still can solve the problem. We can derive everything. So I will be busy with derivation for a while, and I will do it in two ways to quantize a damped oscillator. Good.
Hallo.
Oh, hoi.
Je bent al naar de markt geweest?
Ja.
Wow, lekker.
Mag ik even praten?
Wat zeg je?
Dan is het tenminste rustig.
Ja, dat is waar.
En jij bent al bezig.
Ja, heftig hè?
Mag ik even praten, dames en heren?
Ja, dat is een live college, dus dat moet je ook wel.
Oh.
Oh, hij vroeg nu iets. Geen idee.
Dank je wel. Zo. Where did I stop? Right. Next to that, we will look at applications of this quantization. And there will be a piece about correlations in this oscillator, noise. And we will talk about the famous fluctuation-dissipation theorem, which relates seemingly very different things, namely fluctuations and dissipation. Good. We will derive uncertainty principle, density matrix. It will be all applications of the quantization method we will derive. Good. With that, let me go to next transparency. And let me first define the system we will be working with. Let me talk about classical damped oscillator. Good. Couple of equations, perhaps. Oh no, let me first look at this picture. So what we'll have here? Oh, we'll take a particle in parabolic potential. We know that eventually all possible oscillators can be reduced to a model of a particle in parabolic potential. Since we are kind of a Newton level classical mechanics, I'd like to consider different forces which act on the particle. First of all, its potential force coming from parabolic potential, which kind of drives the particle to the origin. Right Here it is in the equation for time derivative of momentum. Next to that, I would like to have some external force. Why? Well, if I don't apply any external force, the oscillator will stop, and that will be pretty boring. So I need an external force. Right, what is most important today is a friction force, which must be added to describe dissipation. All right, this forces, those are equations for time derivative of the momentum. And right, if you know momentum, you know how coordinate would change. Good. As I said, any realistic oscillator which you can build up, which you can observe in nature, is damped. If one would look at the ideal oscillator, how the deviation from equilibrium, from the origin, would depend on time, well, it will oscillate with the frequency of the oscillator, and it will stay unchanged for a long time. Why? Because energy is conserved. Friction force leads to energy dissipation. So that's what we got. We see that this the amplitude of oscillations is damped and goes to zero at a certain time interval. Let's call it dissipation time. Right, so how to model this friction force? The most widespread friction force which we experience is dry friction force. But eventually, I must be frank, there are very few successful theoretical descriptions of dry friction force, even at the level of classical mechanics. People know too little about dry friction. Strangely enough, it's so widespread, nevertheless. So it would be something for future generations to explore. Here, I'd like to concentrate on a model of fluid friction. In that case, the friction force is proportional with to velocity of this particle. Negative, so it works against velocity. It slows the particle down. And there is a coefficient to characterize this first, coefficient gamma. What I want to discuss now, that would be the simplest model. If I want to find a more realistic model of the friction, should think a bit and figure out that the force perhaps reacts on the velocity of the particle with some delay. So here I've modified this equation, introducing a delay. Tau is delay time, and well, I have a distribution of delays. So this coefficient gamma will depend on delay. Right. It's much more convenient to rewrite this equation in Fourier domain. So instead, I will write Fourier component of the force. It is related to Fourier component of velocity or Fourier component of x. It's just the same. It's a factor of I omega, which comes about. And this friction coefficient will depend on omega. Good. A little bit more general model. Fine. That is an example of classical damped oscillator. And yet another important piece of information from classical physics. This is a very convenient concept, which we will use today. And I suggest you use it in the future because the concept is really nice and general and useful. It's a concept of what people notice and call with this strange combination of words dynamical susceptibility. What is that about? You have a system, linear system. You have a variable which is called x, and you have an action which works on this system. For instance, external force. And that can happen at different frequencies. You can apply external force at different frequencies, and you have different responses, reactions. Since the system is linear, there is a proportionality coefficient, which is called dynamical susceptibility. Good. One can solve the equations which we have and get dynamical susceptibility for our oscillator. Good, we find all these terms that comes from potential energy. This is the mass of the particle. And here we find the friction. All right, so I want to describe very general relation for this dynamical susceptibility, kind of a relation which you can use as a foolproof to check whether susceptibility is correct or not. This comes from the fact that the reaction is always delayed with respect to action. Right? So the reaction knows about force in the past, and it cannot know about force in the future. This is called by a funny word causality. And the manifestation of this that the susceptibility as a function of complex frequency omega is eventually analytical in upper half plane of omega, which means that omega, the imaginary part of it, is bigger than 0. Fine. I kind of miss you, sir. Many of you have been, all of you have been in applied physics building. Then if you are attentive, you know who is this person. Who knows this person? Please type it in the chat. Yes, yes, you're right. Either read it or you know it by heart. It's Ralph Kronig, which, among other things, used to be rector magnificus of this particular university for many years. He was a student of Wolfgang Pauli, and he has almost discovered electron spin, which have been a very big discovery, but a kind of Wolfgang Pauli, being his PhD supervisor, didn't understand this, and the publication was delayed. Nevertheless, Ralph Kronig has made many interesting discoveries and contributions. Kronig-Penney lattice that perhaps you have heard in solid state physics, perhaps not, but what the most important one is that Kramers-Kronig relation. In fact, it's just a piece of mathematics. If you have a function which is analytical in upper half plane, you can find a relation between real part of this function and the imaginary part. Imaginary part, let's learn this. It describes, it gives dissipation. As to real parts, well, we can have lots of real parts here that comes from potential energy, from motion. This relation is universal. It works for any pair of action and reaction. For instance, it works to define refraction coefficient, where action is external field and the reaction is a field in an optical media. So, for instance, the classical application of Kramers-Kronig relation is to find a real part of refraction coefficient if one knows dissipation in this medium. Looks like a piece of matrix. Dissipation, absorption of the light is one property, and its propagation seems to be a completely unrelated property. Nevertheless, by virtue of causality, these quantities are related. Kramers-Kronig relation. Good. We know that. We learn about the use of susceptibility. Let us go on and let us understand that oscillators and damped oscillators as well are not really restricted to mechanics. One can just have the same oscillator with same laws in the world of electric circuits. So let us arrange a damped electric oscillator. How do we do this? In order to make an oscillator, one needs capacitor and inductance. Right. Then I would like to add friction force. And in order to do this, I put a resistor in series. And I need to excite oscillator, so I put a voltage source over here. Very good. So what for equations will I have in classical domain? There is an induction. So voltage drop at the inductor consists of voltage drop at the capacitor. You be in charge of the capacitor. A voltage drop at the resistor and external voltage drop. And the current through the circuit, yeah, it changes the charge at the capacitor. One looks at these equations, one notices that upon the change of notations, we got the same equations as for mechanical oscillator. So it says we have the same physics and write what I want to write down below that, in fact, it can be also characterized by dynamical susceptibility. So the reaction is charge at the capacitor, and action is external voltage source. Right, so this external voltage source will create some current, and proportionality coefficient between voltage and current is just conductance. So I put it here, and I divide it by minus I omega. Well, because of that, this is proportionality between current and charge. All right, everybody is happy with this, I presume. Questions to the chart, and I will outline the difficulties to describe such system in quantum mechanical terms. Well, in order to understand how difficult the difficulties are, let me recall traditional quantum mechanical description. If you work with a single degree of freedom, and well, our oscillator, damped or not, is apparently a single degree of freedom, can be characterized by a single value x deviation. So if we have single degree of freedom in traditional quantum mechanics, we have wave function which depends on this variable. Good, we can have Schrödinger equation for this wave function, and that conserves energy provided the Hamiltonian is stationary. So we have wave functions. We have also superposition principle. The sum of two wave functions is also legitimate wave functions. Right. So what are the features of this description? Energy, as I said, is conserved. So we have stationary states at many energies. And once the system is in stationary state, it will stay over there forever. So there is no way to reach an equilibrium for a quantum system. Unitary evolution. Also, there is time reversibility in quantum mechanics. All equations can be changed. Sign of time can be changed in all equations, changing Hamiltonian and sign of Hamiltonian, and it will go fine. This is in sharp contrast with our life. We don't have time reversibility in macroscopic world. Well, we're all gonna get older. And all these features are absolutely not compatible with dissipation. There have been many creative people are many, and simplest way to display your creativity, just change something a bit and look at the consequences. So there are many attempts to include friction into quantum mechanical description, not in general, but perhaps for a single model. They look at complex variables, say this X could become complex. They consider non-Hermitian Hamiltonians. They have been trying to modify a Schrödinger equation in such a way that it describes non-unitary evolution. Nothing has worked. there is no consistent quantum mechanical description at this level, at the level of modification of Schrödinger equation. So one has to proceed in a different fashion. Let's see how I'm doing with respect to time. Well, that's fine. Right, I promise long break, so it will happen in 15 minutes. Let me solve the problem in general. Let me understand what do we need at least in order to solve the problem. It's kind of simple if you have known the solution already. In fact, the same problem with description of friction dissipation we encounter in classical mechanics, right? In classical mechanics, you also have Newton equations which conserve energy, which provide stationary solutions like oscillator, which never dies, which always oscillates without stopping. In order to understand the friction, not at phenomenological level, but completely, one has to look at microscopic origin of friction. And that necessarily involves many degrees of freedom. In fact, infinitely many. Right. Let us consider, for instance, a big particle which flies in a gas of molecules. Right, if you put it with certain velocity, sooner or later it will stop. There will be dissipation. And what does it mean? The particle collides with molecules. It loses its momentum. It loses energy in the process of these collisions. One needs infinitely many molecules for this. Why is it, sir? If there's finite number of molecules, even a big one, there's still energy conservation for the whole system, right? So the energy of the particle will be distributed between all molecules, finite number of molecules, and the energy would still conserve, so the dissipation will stop. Right, so that sets us also ways to set up quantum mechanical description. Well, we would know how to describe molecules in quantum mechanical language, but perhaps it's even too complex. So one has to go for a simplest solution. So in addition to a single degree of freedom, we need to consider infinitely many degrees of freedom, which is called paths. More physical name is perhaps environment, right? This big particle is in environment which consists of molecules. Right, and the requirement, or perhaps a hope, that such a description should not depend on Bass details. What do I mean? Molecules in this gas can be very different. The gas can have different density, different types of molecules, oxygen, nitrogen, I don't know. It all amounts to certain friction coefficient. So we want a description which doesn't take care of shape of the molecules. We want a description which only involves a friction coefficient. Fine. So let's build one. What do we need? Again, the goal is to describe damped oscillator. So we have this one without dissipation. Operator of momentum, operator of coordinate, we know that. Then next to it we have a bus, and bus is written in the form of simple bosonic Hamiltonian. So there is a set of boson modes, very many, with frequencies omega k, and these are creation annihilation operators responsible for creation annihilation of corresponding bosons in each mode. Right. Next to it, we want to have linear equations. And that means that the coupling between oscillator and these modes has to be quadratic. And any quadratic coupling of this kind, I can write like this. I have an operator x coordinate, and it is coupled to the bosons, to each mode, okay, with some coefficient C, K coupling coefficient, C stays for coupling, right? And the problem which I encounter, which we'll solve soon, is that there are very many of the C's, very many of coupling coefficients. And I don't want to know that many, because I put all the C's just to describe a friction, a single friction coefficient, right? So we need to figure out what are these C's, how to characterize these C's, coupling constants, and the crucial point is to notice that altogether the C is a base form a force operator of friction force. Very well. Then let us, we have a Hamiltonian, let's proceed, let's do something. And in this setup, we will proceed with Heisenberg equations of motions. We don't want to know wave function, so Heisenberg equation is the most convenient way. And also we can directly compare it with classical equations. Good. To apply Heisenberg equation, one has to commute operators with Hamiltonians. For that, one needs to know commutation relations. And, well, that we know. Bosons, commutation relations for bosons, and commutation relation for momentum and coordinate. Good. We do this. We put this commutation relations with our Hamiltonian. Let's see what we get, what kind of equations. These equations are of oscillator. We have seen it already. It's exact correspondence with classical equations. Right? This is operator of force, which is linear combination of these, which is written at the previous transparency. And then I have an equation for base. For each B, there's a separate equation, very convenient. And the operator of coordinate, this coupling constant, works as a source for this equation. All right. Then we can solve. We can solve this equation for B. And this is a solution. So what I did, I rewrote this equation in Fourier components, solve for that. It is crucial to add one small thing, which is eventually zero, infinitesimally small part to this expression. And this, if you look at mass, if you look how to solve this equation, comes about the fact that these depend on the value of x in the past and not in the future. Would I have sign mistake? Would I have plus here? Would be the same equation, but in that case, it would be really crazy. B's would depend on values of x in the future. So let's not go crazy. Let's keep minus here. Good. What we have now is expression for each b in terms of x, and now we can put it back into the expression for friction force, and that's what we get. Proportionality coefficient between operators of force and operators of coordinate. All right, there is quite some expression, and we need to look in more detail to this. Let us see. First of all, let me look at imaginary part of this expression. Why is it true? Because it is immediately related to dissipation. We know from classical physics that imaginary part of susceptibility, and that is what we compute at the moment. Imaginary part of the susceptibility is related to dissipation. So how we do with imaginary parts? If we look at it at first sight, we don't have anything imaginary here at all, except these funny imaginary parts. They're small, they're zeros, but if you recall Cauchy relation, one understands that these small zeros actually produce delta functions. Anytime the denominator gets to zero, very small imaginary part becomes important, and it will give delta function peaks. And that kind of makes sense. Omega is a frequency with which x oscillate, and it excites modes corresponding to this excitation frequency, and energy goes there. Okay, we see that this consists of two parts, which I would call J, with opposite frequencies. Right, so I write this J. And if I take the fact that the modes are discrete, if I take this fact formally, then J would be something crazy, a set of delta functional peaks. No, that's not a way to provide dissipation, to describe dissipation. It is important at this point to make the spectrum continuous, to merge all these delta peaks together. So after that, J will become a smooth function of omega. That's it. Right. And then we have coefficient. We have coefficient between x or derivative and force, and that sets this J. That's J. So one needs friction coefficient here depending on omega. So what does it mean? If we know friction coefficient, we don't fix each C. That's impossible and is not needed. One should not, it should not depend on the details of the mass, which are C's. But we do fix the form like this. This should be expressed in terms of friction coefficients. That's it. We have quantized oscillator, but there is also real part. I have to say something about the real part. And this is perhaps a bit complex concept, but well, we can treat it simply. Real part, eventually a renormalization. One can see it directly by computing that. Well, since imaginary part and real part are related by Kramers-Kronig relation, one can express real part in terms of the same function J, in terms of the same friction coefficient. But that would provide a real coefficient, real coupling between X and force. And that will work precisely in the same fashion as the potential force. It will give it an addition, which will also depend on frequency. That's strange. So how to deal with this? How to understand what is happening? One has to recognize that friction is there, and one cannot remove it. That's why if we would like to assess potential energy experimentally, we won't be able to get this alpha. We can only see the whole combination of that. So this will be observable coefficient, renormalized coefficient. And we don't even care about alpha, which we can observe. Right. So by specific language of renormalization theory, which is applied in many aspects just for us, that value of alpha already with friction is called rest. And that value, initial value, which is just a parameter in the Hamiltonian, is called bare, which is synonym of invisible in this case. So from that, one can already figure out when normalization theory has been developed. It has happened in 50s of 20th century. Why is it so? By that time, people kind of had strict rules, and bare was really invisible, was a synonym of that. While dressed is how people kind of can be observed. People by that time could be observed only in dressed states. Would you make it 15 years more? It would be already quite different. Perhaps your grandmothers can tell you something about 60s. It's eventually was very interesting time. So at that time, bare was not more a synonym of invisible. Very good. So we find the relation between discipline Fine. Very good. That's me again, only partially. No, in my total. Renormalization. We have discussed it. We understand that the real part, which comes from the friction, just adds to potential energy. And what we see is a quantity which incorporates the space, which we can safely disregard. It just means that we need to use observed the observed coefficient of potential energy. Right. Let me do the same in a different fashion. So again, we quantize the oscillator, and let me notice that the way we did it before the break was not actually democratic one. Why? This is an oscillator, and those are oscillators. But we did not treat them democratically. We have artificially separated a particle, which is an oscillator, and its environment. But as we have already seen from this renormalization, this separation is artificial. Environment affects particle and particle affects environment. So this calculational scheme can be democratized. How would I do this? Well, I would just take all oscillators I have, and I would make a new set of oscillators, which has slightly different eigenfrequencies that stay still. They would cover all continuous spectrum of the bass. It will originate from the bass. And I would also incorporate the coupling. So I would end up with a Hamiltonian like this. Well, now I'm happy. All oscillators are treated in the same way. Democracy has won, but now I cannot find the variable I'm looking at. There's no this variable in the Hamiltonian. How can I proceed? Well, there is a marker for this variable. There is an important marker, namely the external force. So if I add an external force to this Hamiltonian, I will understand the variable which I will look at. Yeah, that's an important point to understand. External force is a marker for the variable I look at that can contain infinitely many degrees of freedom, but my force is applied to this particular oscillator. And that's how I figure this out. Very good. Now I want to relate this operator of displacement x and these little infinitely many guys b's. The system of equations is linear, so the relation must be linear. That's how I put the general relation. So there is a contribution to X from each mode, which I will denote with also C, but a capital C. Right. These C's can be in principle obtained by diagonalization of this Hamiltonian, but that's kind of rather complex. It is faster and more constructive to work out this quantization from very beginning. So we will start with this Hamiltonian and look at the consequences. Let's do this. Right. Equations of motion. Since we have only B's, these equations of motions can be written in a simple fashion. After all, it looks like this. For each B, we have a separate equation, and that equation contains external force as a source. So let me compute B's through the force. Here, what I have, right, imaginary, infinitesimally small imaginary number, has to keep it, and has to make sure that this is, B's depend on force in past rather than in future. Good, coefficient Cm come here. Then I substitute this into equation for X. Yeah, this is what I get. So I get proportionality between external force and operator X, but it is nothing but susceptibility. Let me recall the definition of susceptibility. We work at something with external force, we got reaction. The susceptibility is the coefficient between. Good, so we take real part of this expression to obtain this. Let's see, it works only at positive frequencies. Right. Fine, so how does it work? We cannot know all the C capitals as we did not know the small c's. But we don't have to know what is what one needs to know and what is the essence of quantization procedure. We can relate squares of C's at certain energy with imaginary part of susceptibility at this particular energy. And that solves the quantization of damped oscillator. So we get quantum description, and we can obtain this quantum description precisely from the classical one. So we use susceptibility obtained from classic solution of classical equations. We plug it in here, we got C squared m, we got this combination, and that will enable us to do everything, to reveal quantum properties of the oscillator. Right. So at this point, we have quantized the damped oscillator. We quantize it in two ways. In first way, we kind of look at this oscillator separately and find the relation between friction force and displacement. The same can be done in a different way. We can democratize oscillators. We can put a marker to a degree of freedom which we look at, which is subject to external force. And we can find the proportionality coefficient between displacement and this external force, which is susceptibility. So now, if you know susceptibility, we have quantum description of the damped oscillator, and in fact, of any linear system. Any linear system can be treated in the same way. Right, so let's go to applications. Let's see what we can learn out of that. Right. First of all, I would like to talk a little bit about time-dependent fluctuations. One can also call it noise. I believe that you have heard about about noise at signal, whatever this course is called, and course about signals. You have heard about noise, Josephson Nyquist noise in other courses of physics. Whatever the quantity to look at, this is definition of noise spectrum. What do I have here? I have correlations of a certain variable x in time. Averages of x, the product of x taken in different moments of time. Right? If I take Fourier transform of this, I got the spectrum. What is the spectrum? Is a contribution to fluctuation of x coming from certain frequency region. All right. I wonder if I kind of activated your memory, if you can relate this definition to other definitions of noise spectrum. Please tell me about it. If you cannot, it's fine. We can talk more about this. But let me know whether it works. I have again a problem with the chat. I have to stop share. Yes, Mohammed, it implies that the noise is Gaussian, at least for linear system and for small deviations of this x from equilibrium. It's kind of general mathematical theorem, which is called central limit theorem, and which has kind of much manifestation in physics, means that almost every distribution of small deviations is normal distribution, Gaussian distribution. Here it looks like statistical noise shown. It is so that's how noise is defined in statistics. in signal processing, in everything related to statistics. Good. Spectrum is important. One talks very much about white noise, and for white noise, the spectrum does not depend on frequency. But okay, it's only a particular case of noise. It can depend on frequency in general. Let me get to screen sharing. Right, so we will compute this noise, and we do it in a bit general case. I also want to take into account finite temperature of the bus. How can I do this? Well, the time I will average over operator B's. I will put here Bose distribution, field factor corresponding to Bose distribution with certain temperature T. Good. So we are interested to learn what is this noise in thermal equilibrium, and how to proceed. Well, it is pretty much straightforward. If we notice that our variable x is a linear combination of creation and annihilation operators, well, it depends on T, but we know how these operators look like in what is the relation between operators in Schrödinger picture and in Heisenberg picture. It's just time-dependent exponential factor which comes by. Fine. So we just substitute it all into x, and x will substitute here, and we will take average. Let's see. Let me get some more steps of this deviation. All right. After substitution, we have already the squares of Cm. Right. We have averages of operators in time domain. But now it's time to implement the, and now we can average over bosons. So that's where the distribution of boson distribution will come. Right. Okay. Then we can take integral over time. Yeah, we have two delta functions, which has a kind of obvious meaning. As oscillations, fluctuations, and frequency omega are related to the modes which have the same frequency. Right. The only point I've got, again, an awful summation over all modes. I can greatly simplify this if I use the relation between imaginary part of susceptibility and Cm. Let me find it again. Here it is, not to forget. So instead of this delta functions, I can substitute susceptibility and see what I get. Noise spectrum fluctuations appear to be proportional to imaginary part of susceptibility dissipation at this particular frequency. And what I get instead of this expression, if I substitute omega m to omega, that is a factor which comes from Bose distribution, it contains the temperature. So, nice. Right. The relation of this type has been discovered already. Okay, quantum mechanics was quite mature science by this time. Cullen and Welton was a great achievement, and kind of they say they call this in a such awfully long name. It's really very long and awful for English air. Fluctuation-dissipation theorem. In order for people to call it simply Cullen-Welton theorem. But for some reason, it doesn't work. So everybody knows it as fluctuation-dissipation theorem. And it holds not for any systems, not only for our model of bosonic bands, just for any system, as far as we are talking about small deviations, as far as we are talking about normal distribution of noise. It is general. And this theorem relates dissipation properties of a system and fluctuation properties of the system in a very simple fashion. Spectrum fluctuations is proportional to imaginary part of the susceptibility dissipation at a given frequency. Good. There are two limits of the noise of fluctuation dissipation theorem. First limit is classical, and this is achieved at high T. And in this case, we can use approximation of hyperbolic cotangents, which is just inverse on this. And then H bar magically cancels here and here. So we have an equation which doesn't contain an H bar. Very good. It means that the equation should be the same in classical limit. Right. So at frequencies which are bigger, sorry, at temperatures which are bigger than corresponding frequencies, the noise is classical. And this is thermal noise. That's what we normally assume from noise. It is proportional to temperature. The hotter the body is, the more noise we can have. All right. Another limit is a limit of low temperatures or high frequencies. In this case, H bar omega is much bigger than KBT. Fine. Noise is quantum. H bar is in front of this. It is proportional to Planck constant. And, well, it is still finite. So there's quantum noise persists even at ground state, even at zero frequency. Sorry, even at zero temperature. And, well, again, it is proportional to dissipation, to imaginary part of the susceptibility. Very good. That was fluctuation dissipation theorem. Very strong theorem, very strong and deep piece of knowledge which relates fluctuations and dissipation. Right. Let me now talk about uncertainty. You've been told much about Heisenberg uncertainty relation in your first quantum course. We also recently looked at it when we talked about coherent states. It was just a lecture ago. And what we have learned or remembered that uncertainty of x, or whatever variance of x, and variance of momentum, if you make a product of this, it always exceeds some critical value of Planck constant. So one cannot have well-defined x and well-defined momentum simultaneously. Good. Now let me check this relation. Let me examine this quantity for a damped oscillator. Right, and I will do it for zero temperature just to keep things simpler. Well, we understand what are fluctuations, what are some of fluctuations of the oscillator. Good. So what I have to do in order to compute the total fluctuation, I need to integrate over spectrum. This is sometimes a point of misunderstanding. It is direct application of Fourier transform, but okay, you learn Fourier transform, you forget about this, and especially about its application to the noises. But please, if you have a problem with this, please try to do it at home by hand by doing Fourier transforms. The instant fluctuation of any variable in a given moment of time is eventually an integral over the spectrum. All right. Wonder if any questions about this. I lost chart window again. That really drives me crazy. Chat. Right, no questions at this point. Let me get back to my open board. Right. Sure, but what we know what the spectrum is, sir, we need to substitute imaginary part of susceptibility in this equation. Integration here is from 0 to infinity. Imaginary part is actually odd at odd function frequency. So if we integrate it from minus infinity to plus infinity, we just get 0, right? So imaginary part at positive frequencies. Right, that's what I get. I need a fluctuation of momentum that I could do very simply if I notice that momentum is just velocity times mass. Good. So I substitute this equation in Fourier domain over here. So eventually I need to integrate almost the same quantity, but with a different weight, with a weight proportional to omega squared. So here there are some integrals which express these quantities, and we will do it for a model in hand for damped oscillator with a bit of friction. Good. What would be convenient quantity to define? It is a quantity which characterizes quality. Its inverse quality factor. So it's proportional to the friction. The more friction they have, the bigger kappa is. All right. And roughly it shows, quality factor shows how many oscillations the oscillator does before it stops. So inverse quality factor is just inverse of it. So if K is bigger than 1, then we don't have even a single oscillation. We have just exponential damping of X. Right. So one can make the substitutions and let us see what I have. That's X versus inverse quality factor versus inverse quality factor, and normalize it to the value of X, the fluctuation of X, which is actually 0-point fluctuation. I have 0 temperature, so all fluctuations in the oscillator are quantum, 0-point fluctuation of X. Right. So it depends on K. It doesn't look very comprehensive, so I'd better plot it. This is this plot with green line. And I see that X, fluctuation of X slowly drops down with increasing friction. Right, kind of friction stops the oscillator more efficiently, so it is not surprising. Then I compute the same integral for momentum. I've got to cheat a bit, and this is because this integral formally diverges at high frequencies. Nothing is bad with this divergence. It can be taken care of if one recalls what I said in the beginning of this lecture. There's always a delay between velocity and friction force. If one takes this delay into account, introducing some cutoff frequency, that's gonna be finite expression. And let us see, yeah, it's this red part. So this is a fluctuation of momentum quickly increases with increasing friction. That can be a little bit counterintuitive. Anyway, friction is supposed to stop everything. So why doesn't it stop momentum? Well, it's already quantum effect. It becomes more localized in the X domain, so it should increase in momentum. Good, but my point, my goal is just to assert this uncertainty. Eventually, I'd like to look at the uncertainty in the oscillator. And if there's no friction, it is conveniently one minimal uncertainty. But if the friction is increased, well, it actually grows. It grows very slowly, I believe, as a log of K, but it goes. It means that the oscillator with friction has larger uncertainty than Heisenberg relation would imply. So kind of friction is harmful for uncertainty. Very good. And if friction is big, if quality factor is infinite, if you have only friction, uncertainty is just tremendous. Could go to infinity. That's right. Then let me look at it at the damped oscillator from yet another point of view. Let me look at density matrix of it. We have discussed it in the first lecture and in some problem solving session, I believe. But let me shortly, very shortly, to refresh density matrix. It can come from two different things. One talks about density matrix when one has statistical mixture of the states, like an ensemble of atoms, which are in different states I, with some probabilities, and we want to characterize this ensemble, and we use density matrix for that. So it can be expressed in terms of wave functions. Wave functions would depend on coordinates. Each of the two wave functions, so density matrix would actually depend on two coordinates. Right. Another definition of partial trace, and that would be a kind of the definition which is important for us, is the partial trace, which means that we don't want to know about some degrees of freedom, and we trace them. Right? This is an application of a wave function which depends on two variables. We trace it over right. Tracing means kind of summation over diagonal elements. I and I here the same. And we have density matrix. In any case, for to compute an expectation value of any operator, one can use density matrix similar to quantum description for a pure state. For purely quantum mechanical states, square root of density matrix is the same density matrix. So eventually, if one has density matrix, one can write purity test. One can compute trace of square root of density matrix. Then, if this trace of squared is 1, we have absolutely pure state, we have quantum mechanics. If it is smaller than 1, it means that, we involve very many degrees of freedom of our description, and that makes the system more classical. Good. That was reflection of density matrix. So let me quickly derive it for our system for damped oscillator. It has been done in the book in quite some detail. Let me just make it in a short, in a quick and dirty way. Let us assume this dependence of density matrix on coordinates. So, it is has something to do with normal distribution, which is Gaussian function, which is characteristic for linear systems, so for small noise. Good also for ground state of an oscillator. Ground state is just a Gaussian function. Right, so we assume this form, And now with this form, we can compute averages. We can compute variances of momentum and coordinate. With this, we can eventually express coefficients A and C in terms of these averages. So I've got this expression in full glory. This is density matrix of a damped oscillator expressed in terms of its of the variances of momentum and coordinate. So here it is. Right. What to do with this? If this and this just satisfies Heisenberg relation, these terms cancel each other in such a way that it becomes the product of two oscillator wave functions. Don't remember the coefficient here. So it's a product of two wave functions. Each is a ground state of the pure quantum mechanical oscillator. So it's a pure state. Right, so now we can use it, this function, to run a purity check for the ground state of damped oscillator. Right, we can compute the square of the separator trace. That's what we got. Again, if uncertainty is ideal, this is quantum. If uncertainty is bigger, as in oscillator restriction, then the system becomes more classical, right? So the more damping we have, the more the system in hand, damped oscillator, deviates from purely quantum system. Let me summarize what we have. We have learned how to quantize an oscillator. The computations, the deviations we use, the quantities are not specific to the oscillator. If we know susceptibility, we can quantize our system. So we can quantize any linear dissipative dynamics. One can quickly do the same for multiple degrees of freedom. Take us two oscillators. Yeah, basically we will have to do the same, but now we have two variables. We have susceptibility, which is 2 by 2 matrix, and we can apply everything what we done for two oscillators. So for many, or for infinitely many oscillators even. Right, we understood that realistic quantum mechanics with dissipation, necessary involves infinitely many degrees of freedom. And those are degrees of freedom we observers, we actors in this world, just don't want to care about. So one can say that we are arrogant or ignorant But well, that's not even our choice. We are humans. We cannot, you know, encompass everything. We cannot encompass infinities, right? So for our work, we work with few degrees of freedom. And as we have seen from our calculation, the states, quantum mechanical states with we work, are eventually impure. Any interaction with environment, any dissipation, any friction would make them impure. So, for instance, our attempts to build up qubits, to use pure quantum mechanics are hampered by this fact. One has to think about the coherence in qubits, interaction with environments. Again, because dissipation, whether you want it or not, is just the most universal feature in our world, always persists. One can only try to make it smaller, to make it safer. So that was the conclusion. We have quantized damped oscillator. So, and did I do it in time? Almost. Sorry for a small delay. The lecture is over. Let me check the chat. No, there's nothing more in the chat. So thank you very much for your presence. See you next time. Bye.
Bye.